Hello, so in this video we will talk about the function of two random variables, which is the difference. Okay, so again we have the starting definition that x is some random variable with some PDF and y is some random variable with some PDF, and we can assume that they are independent here, and we have z is equal to x minus y, and we have to find the PDF of z. So what is the CDF of z? CDF of z is the probability that x minus y is less than z, which means that we have to integrate the joint probability distribution function of x and y in the range when x minus y is less than z. Okay, and this actually translates into the limits of x, limits of y to minus infinity to infinity, and limits of z from minus infinity to y plus z, because x minus y less than z means x is less than y plus z. Okay, so this is my limits here, and then after we differentiate, note that the letter z is only for our uh, x variable. So the after differentiation, the integration with respect to x goes away, and we are left with just y f of x at f of x and y at y plus z and z. So this is the x value, this is the y value. From here to here, we have already seen in our explanation when we were explaining the quotient of x and y, how to come from this and this. This comes from the fundamental theorem of calculus, and the interested viewer can go to that and see how we go from this and this if needed. Okay, and for the discrete case, this integration is translated into this summation. This dy should not be there, and we have the same story here. We have x is equal to y plus z and y is equal to y, and we sum over all the values of y. There is a special case here where there's a special case when we have x is always positive and y is always positive. If x is positive and y is positive, note that z does not necessarily have to be positive, because z is x minus y. So whenever x minus y is greater than 0, then z is greater than 0. Whenever x minus y is less than 0, we have z less than 0. So we have this limit and we have this limit. Okay, for z greater than 0, we have our normal expression here. For z less than 0, note that if we put y is equal to 0 here, then since x is less than y, then we are saying that x is actually negative. So we have to start with, for y, the value of minimum value of x corresponding to that y. So for example, minimum value of x is 0, and our z is x minus y. So this means the minimum value of y should be negative z here. So negative z, note that negative z is actually positive because z is negative. Okay, so the limit of y will be from negative z to infinity. Okay, so now let's see two examples here. One example is for discrete. The first example is for discrete random variable. So for discrete random variable, we have x is a Bernoulli with parameter p, y is Bernoulli with parameter p, which means that x can only be 0 and 1 and y can only be 0 and 1, which means that z can be negative 1, 0 and 1, because if you see all the combinations of 0 and 1, subtracting them, then you will get three values: 1 minus 1, 1 minus 0, 0 minus 1, and 0 minus 0. So for all those four values, we have this PMF here. So for example, whenever we have z is equal to negative 1, we have, which means x is equal to 0 and y is equal to 1, which means since they are independent, we can times them or multiply them. So that's why we have 1 minus p and p here. And whenever z is equal to 0, we have two possibilities: x and y both 0 and x and y both 1. So that's why we have this possibility and this possibility. And whenever z is equal to 1, which means x is equal to 1 and y is equal to 0, we have this possibility, and this is equal to this value. And if you add these three, you will surely get a 1. Okay, now let's do a continuous example. So for continuous example, we will assume that our x is exponential with parameter lambda, y is also exponential with parameter lambda, which means the probability, the PDF is lambda e minus lambda x and lambda e minus lambda y. y, and x is always greater than 0, and y is always greater than 0. Okay, now this is exactly the same case which we talked about here. Okay, so in order to solve this, so we have to check, we have to say 0. So this is simply 0 to infinity, um, lambda squared, because this lambda and this lambda, and then we will have e to the minus lambda y plus z, and e to the minus lambda y dy. So this is straightforward integration, and you should get 1 over 2 lambda times lambda squared times e to the minus lambda z, which is equal to lambda over 2 e to the minus lambda z. Okay, and for our other case, we will have minus z to infinity. Again the same story, e to the minus lambda y plus z, e to the minus lambda y, this times dy, which is equal to lambda over 2 e to the lambda z. So combining this guy and this guy, we will get, uh, 1 over 2 lambda e to the minus lambda absolute value of z. This is my fz of z. Okay, okay. So I'm skipping the integration part because it's straightforward to integrate. There is no integration by parts, or there's no substitution. All we have to do is we have to remove this lambda squared out of the integral, and we have to remove this e to the minus lambda z out of the integral, and use the same upper limit minus lower limit after integrating e to the some constant times y. Okay, okay. So this is it for, and you can check that this actually integrates to 1. Okay, so in short, in summary, what we have done is we have found the PDF of z in both in discrete and continuous case when z is equal to the difference of two random variables. Okay, hope it was easy to understand, and thanks for watching. Hope you liked the video.